So it looks like I forgot to record, which is why there's so much written upon the page. If you would recall, last time we wanted to find the rate of change of a function of two variables in a particular direction that wasn't just x or y. And this is, of course, happening at a point. The derivative is a local calculation. What's going on at this point? We've said some important things like rate of change. Rate of change should make us think derivatives. Function of two variables means first partials. Last time we looked at this direction v, so 2i plus 5j. So I'm going to be using this in some calculations, and I only care about the direction. We're just using 2i plus 5j as a convenient way to describe the direction. I could have used 20i plus 50j. That's the same direction. I could have used, I can't multiply by something else. I could stick zeros in the end, but then that's the limit of my arithmetic calculations today. So I said, I only want the direction, so we're going to make it a unit vector. So automatically we're suspicious, right? It's Scooby-Doo. You know, y'all are the Scooby Gang. You know, this person over there was the sheriff, and I'm the other character. So you're like immediately suspicious of my motives. It's like, oh, well, clearly this one is the villain, because there's only two other characters besides the Scooby Gang. And one of them, we said, it looks like a good guy because he's drawn like Superman with a big old square chin and all kinds of other trappings of the good guy. Meanwhile, you've got this other character, some variation of Snidely Whiplash. Like, oh gosh, I wonder if he's the villain. Turn around to the sheriff, say, Sheriff, just arrest that dude. He's clearly the only person behind it. And the sheriff's like, oh, well, I don't know. How can you tell that? It's like, oh, well, how many other people are in the town? And the sheriff's like, oh, none. Everybody that's present is here. That's efficient storytelling. It's good. Anyway, so we want a unit vector in this direction. Because I only care about the direction. I don't care about how big that direction is, or how big that vector is. Since we got first partials, and we've got vectors that showed up, that should immediately make us think of gradients. So we build the gradient of the function. That's going to give us a vector. And we're going to find the gradient at that point. This is going to tell us the direction of maximum increase. Along the contour, zero increase in the function. Perpendicular to that contour, in the direction of the gradient will be the direction of maximum increase. So we got two vectors from R2. We are looking for a rate of change, which is a scalar. This tells us to use the dot product. So I can take these two vectors, combine them, and come up with a scalar. On the list of things that we can do with two vectors that will produce a scalar, that's the only thing we got. So by process of elimination, mechanically, dot product is the only thing that we can do. So we find the dot product and we come up with a scalar. We need to be able to interpret this scalar in the context of the problem. If we go in the direction of 2i plus 5j, this is how much the function is going to increase. Approximately. This is the slope of a line tangent to this surface in this direction. So that's the slope of a line tangent to that surface in that direction. If I take a line in the direction of 2i plus 5j, and I put it tangent to that surface, it's going to increase by 516 over the square root of 29 because random numbers are random. And in that direction, that's going to be my delta z over delta v, that direction. So now the question is, why does a dot product make sense in this calculation? Why does it make sense for us to use the dot product for this calculation? Think about what else we know about the dot product. As I remind you that this gradient is the direction of maximum increase. Remember that the gradient is the direction of maximum increase. if we consider a contour, we think tangent to the contour, that's where the value of the function is constant. So if we're moving tangent to the contour, the delta f is 0. But if we make the gradient, oh, I just mixed up the colors yet again. The green gradient's here and then green tangent's over here. If we're perpendicular to the contour and is perpendicular to the tangent, that's going to be our maximum in. If I pick some direction in between tangent and maximum, then I have to figure out how much between the 0 and the 1. I need some multiplier between 0 and 1. The 0 is 0, no change, and times 1 is maximum change. We're making a coefficient. We need a coefficient between 0 and 1 to indicate what percentage of the maximum. If I've got a vector, if I pick a direction that's close to the tangent, say with a small angle theta, like 3 or 4 degrees, I should expect my delta f to be small. The most we're going to get is if I pick 90 degrees. That's when our cosine of theta is equal, cosine of 90 is equal to 1. That's going to be our maximum coefficient. If we get something in between, we're going to have some coefficient between 0 and 1. It'll be close to 0 if we're close to tangent, and it'll be close to 1 if we're close to perpendicular. Cosine of 90 is 0. Did I say that backwards? I said that backwards. So instead of, so we get cosine of 0 is equal to 1. So if our angle between our vector and our gradient, see, I got myself with the green thing. This is why the color matching matters. Because I did this same thing last semester. I was using red and blue. I did blue and then I switched them, and then all of a sudden I just switched them in my mind. I looked at the green part and it's like, oh, ah. So this is where 1 and what? So wait, cosine of 0 is how much? 1. Ah, that makes sense. So if our theta is 0, that means we're going in the direction of the gradient. That means we're going to be having our maximum change in f. And what's our cosine of 0? Since I keep forgetting, 1. What happens as theta increases up to 90? It's 0. When theta gets to 90, cosine of 90 is 0. And that makes sense in the picture because now our change is 0. So now the only question is, did I deliberately reverse those to see if anybody was noticing what the f I was talking about? We'll never know because I'm a professional DM. And you just never tell your players the lore. I don't care how cool you think it is. Don't answer the unanswered questions. So think once again mechanically about the dot product. A dot B is the magnitude of A times the magnitude of B times the cosine of the angle between them. If we are going in the direction of the gradient, our angle is 0. That means we are going to get maximum value. Cosine of 90 is 1. If our direction vector and our gradient are going in the same direction, the angle between them will be 0. And so we'll have maximum rate of change. Anything off of that, anything less than 90, anything more than 0 is going to decrease how much of the gradient we're going in, how much direction the gradient we're going in. Up to 90, if we're 90 degrees off the gradient, we are running tangent to the contour, which means that delta F is 0 and cosine of 90 is 0. Any questions? This is what the dot product tells us. A dot B contains the information how much of A is going in the direction of B. How much of our change is going in the direction of this vector. That's why it makes sense to use the dot product. That's why we need a unit vector, because I just want that direction, not the magnitude. If I multiply this unit vector by 2, I'm going to multiply this whole thing by 2. Any questions? Yes. We don't need to worry about the cosine because I don't know what the angle is between these two vectors, although we could figure it out at this point. So we're not using the cosine because the cosine is contained in the dot product. Right. So I did the calculation by finding the sum of the products of the corresponding components, but A dot B is the magnitude of A times the magnitude of B times the cosine of the angle between the vectors. So the cosine of theta is contained in the dot product. That's why it didn't show up until I drew the picture and reversed the cosine of 90 and cosine of 0. Any questions? So today ends with the opposite instruction of yesterday. Yesterday was the instruction was, here's something to think about. Go think about it. The instruction today is the opposite. Here's something to think about. Don't think about it. You need to put this away and let this sit in your subconscious. Don't actively try to think about it. You might mess something up. Just let it go. Let it sit. That's going to do it for today. I'll see y'all on tomorrow. Everybody have a good day, and thanks for playing.